Good day and welcome back for the third installment on Lagrange multipliers. At this point in our series of videos, we've introduced kind of the underlying concepts and we've illustrated them with multiple examples. And what remains through this video and the next few is just going through and practicing additional examples. And as this method of Lagrange multipliers is typically a sticking point or a challenging topic for students, I really want to make sure that we go through enough examples to help you understand the material as well as possible. So the given problem asks us to find the extreme values, i.e. absolute maximums and minimums, of a function of two variables subject to the constraint x squared plus 2y squared equals 6. So once again, this is an ideal scenario for us to use Lagrange multipliers. Our constraint function, coming from the ellipse equation, is x squared plus 2y squared. And just note a couple quick partials. G sub x is 2x, g sub y is 4y, f sub x is 2xy, and lastly f sub y is x squared. Lagrange multipliers will give us a system of three equations to work with. Generally we would have gradient f is lambda times gradient of g, along with the constraint x squared plus 2y squared equals 6. So putting this in terms of partials, from the gradient of f equals lambda gradient of g. The partials with respect to x would give us 2xy is lambda 2x. The partials with respect to y implies that x squared is lambda 4y. And our constraint is x squared plus 2y squared is equal to 6. So remember, we want to work with these gradient equations until we have enough information to substitute into the constraint equation and actually solve for something. Now I'm going to just go back to one of our previous techniques. If we focus in on this first equation, 2xy equals lambda 2x. There's only two possible ways this equation can be satisfied. One of them, note, is if y and lambda are equal to each other. So y could be equal to lambda, or note the other way that this could be satisfied is if x is 0. And I do want to kind of caution you to be careful. A common mistake for a problem of this form is to just immediately divide both sides by 2x and conclude y equals lambda is the only possibility. But remember, when you divide by 2x to come up with this y equals lambda, you're assuming x is not 0, which always leaves open that possibility for x to equal 0. So let's go ahead and see what that gives us. What we want to do once we've garnished this information from the first equation is substitute it into the second equation. It's this nice logical progression, just like with critical points. Work with one until you have enough to plug into another. So y equals lambda, that needs to go directly into the second equation. We can't bypass that fact. So if we go ahead and we bring that information down, so y equals lambda into the second equation, x squared is equal to y times 4y, so 4y squared. And note, that's actually ideal. We can replace this x squared in the gradient, in the constraint equation, with 4y squared. And that gives us something that we can work with. So now, note this logical progression once again. So working our way down vertically, substituting into that constraint, we would have 4y squared plus 2y squared is equal to 6. Where we have substituted in 4y squared for x squared in that constraint equation. And note immediately this simplifies rather nicely. 6y squared is 6. Y squared is 1, which means y is equal to plus or minus 1. And then we now need to think about those corresponding x values. So if we come back to that x squared equals 4y squared, what we will end up with is x squared is equal to 4 times y squared, so 1, which means x squared is 4, so x is plus or minus 2. And just think for a moment, how many potential points of interest does that give us? And I agree, hopefully, that gives us 4 potential points of interest. When x is positive 2, y can be positive 1 or negative 1. When x is minus 2, y can be positive 1 or negative 1. And remember, we need to evaluate our function at each of those points so we can determine where the largest and smallest outcomes occur. In recalling our definition of f as x squared y, f of 2, 1 is 4, as is f of minus 2, 1, whereas f of 2 minus 1 and f of minus 2 minus 1 are both negative 4. And at this point, we cannot make any conclusions in terms of absolute maximums and minimums. What we have learned is when y is equal to lambda, which we got from this first equation, we slowly progressed through to find these 4 potential absolute maximums, absolute minimum locations. We need to do the same thing with x equals 0 to make sure we're not missing anything. Now, the nice thing about x equals 0 is note, you don't need to worry about substituting that into the second equation. X equals 0 immediately gives you something you can work with via the constraint. So if x is 0, the constraint becomes 0 squared plus 2y squared equals 6. So that y squared is 3, or y is plus or minus the square root of 3. So when x is 0, y is plus or minus 3. That gives us 2 more points of interest. We could have 0 positive root 3 and 0 negative root 3. And we need to know what the function value would be at those points. But because our function is x squared times y, if x is 0, the outcome will simply be 0. So in terms of our list of potential absolute maximum and minimum values, there's the zeros, positive 4, and negative 4. And I just realized that there was a typo earlier. This minus 4 with f of minus 2, 1 really should have been a positive 4. So hopefully you were yelling at me through your screen. And we have the absolute max and the absolute minimum. And you do not need to rewrite absolute max and absolute min a second time, as long as it's clear that you've included all of these inputs where those absolute maximums and minimums occur. That finishes up the material for this video. In the next video, we will explore how we can combine Lagrange multipliers with this extreme value theorem that we encountered in the previous section. So stay tuned and take care.